Hello students, in previous lecture we have studied about the buffer solution and types of buffers. Buffers are nothing but these are the solutions which restrict to change in pH even though addition of strong acid or strong base into it, or even that solution get diluted by addition of water. The pH of that solution does not changes. That solution is called as buffer solution. Then buffer solutions are of two types, that is acidic buffer and basic buffer. Then see here how buffer does not changes its pH even after addition of acid or base or water into it. Then that is the buffer action or mechanism of that buffer. Then we will discussing on only mechanism of acidic buffer. And that is also known as buffer action. Taking one of the example of acidic buffer, we will discussing on buffer action. Then for example CH3 COOH and CH3COO Ne. It is a mixture of these two solution in aqueous medium is act as a acidic buffer. In this buffer, the CH3COH is a weak acid, that is it is a weak electrolyte, and here it is a salt of, it is a sodium acetate is a salt of, that is acetic acid, that is weak acid, and NaOH, that is strong base. Therefore it is a strong electrolyte. Nature of this salt is strong, and then in aqueous medium CH3COO Na, that is sodium acetate, it dissociate completely, and because of it is a strong electrolyte, strength of sodium acetate is greater, therefore it dissociate completely to gives CH3CO minus plus Na plus in aqueous medium. And here the acetic acid in aqueous medium, it dissociate feebly because it is a weak electrolyte. Then it dissociate into CH3CO minus plus H plus or hydronium ion. That means when H plus ion of acetic acid, then it reacts with water to give hydronium ion. Then see here this solution of buffer which contains these ions present in it, that is CH3CO minus, Na plus, and H3O plus ion, as well as here undissociated molecules of acetic acid are there, CH3COOH. As sodium acetate is strong electrolyte, it dissociates completely, therefore molecules of sodium acetate are not there in the solution of buffer. That means overall that solution of buffer contains acetate ion, sodium ion, hydronium ion and unionized molecule of acetic acid, that is weak acid. Then the acidic nature or basic nature or pH of that substance or solution is depends upon the hydronium ion or OH minus ion present in the solution. Then here the pH of that buffer is depends upon the concentration of H3O plus present in it. That means there is a fixed amount of molar concentration of hydronium ion which determines the pH of that acidic buffer. Depending upon concentration of H3O plus, molar concentration of H3O plus present in the solution, it determines the pH of that buffer. That means here in this solution hydronium ions are there, therefore the pH of the buffers, that is acidic buffer, is less than 7. That is, the solution is acidic in nature. The pH of that acidic buffer, it does not changes even after addition of strong acid or strong base or water into it. Because see here, if the hydronium ion concentration remains constant, then pH of that substance does not changes. That means concentration of hydronium ion, it remains constant. Then pH of buffer does not changes. And that concept is used in the buffer action. Then see here, there are 3 conditions. That is, first condition, if we add strong acid like HCl is added into it, then see here, already there are CH3CO minus, Na plus, H3O plus and CH3COH molecules are there in the buffer solution. And when HCl like strong acid is added into it, as HCl is a strong electrolyte, it dissociates completely to gives in aqueous medium hydronium ion plus Cl minus ion. That means in aqueous medium, that is buffer solution, in which the concentration of number of hydronium ion increases. But see here, hydronium ion when increases, then pH of that buffer is disturbed or changes. But buffer has action to restrict the pH, to restrict the change in pH of that buffer even after addition of strong acid. Then how to maintain the pH of that buffer? Here the number of H3O plus ion increases, to which here CH3COO minus present in the buffer, it reacts with H3O plus ion or H plus ion and it gives CH3COOH plus H2O. That means the excess number of H3O plus ion when strong acid like HCl is added into it, that excess H plus ions formed due to the dissociation of strong acid, that is HCl. Then that excess H3O plus formed here, it readily reacts with CH3CO minus ion present in the buffer solution, and it gives CH3COH, that is unionized, undissociated acetic acid solution. That means here the excess H3O plus ions are consumed here. Therefore, there is no disturbance of concentration of H3O plus, and the concentration of H3O plus again remains constant, and pH of buffer does not changes even after addition of HCl, small amount of HCl into it. It is because of the reserve basicity property of acetate ion present in the buffer solution. That means that acetate ion has reserve basicity property which readily neutralizes the excess hydronium ion or H plus ion formed due to the HCl. Therefore, the molar concentration of H3O plus ion remains constant. It does not get disturbed. Therefore, pH of the buffer remains constant or it does not changes. Similarly, if strong base like NaOH added into buffer, then as NaOH is a strong electrolyte, it dissociates completely to gives Na plus OH minus ion in aqueous medium. And here, as NaOH is a strong electrolyte, it gives more and more OH minus ions. Therefore, here the solution in which H3O plus ion is already there, then OH minus ion concentration increases due to the addition of strong base into the buffer, and therefore the solution may becomes basic, but the OH minus ion concentration, which is OH minus ions which is formed after dissociation of NaOH, that readily combines with acetic acid or unionized acetic acid molecule in aqueous medium, and it gives CH3COO minus and H3O plus, that is H2O. It gives H2. That means here the excess OH minus ions are consumed because of unionized acetic acid molecule, and the concentration of H3O plus is again remains constant, and the pH of the acidic buffer remains constant. It does not changes due to the acetic acid, the property of acetic acid, that is reserve acidity of that acetic acid molecule which neutralizes the excess OH minus ion formed due to the dissociation of NaOH when NaOH is added into it, and pH of the substance or buffer remains constant. Similarly, even after dilution of buffer, that means if buffer get diluted, that means excess water is added into it. Then water dissociate into H3O plus and OH minus ions. But here the H3O plus in water, it reacts with acetate ion. That acetate ion neutralizes the H3O plus of water, and the concentration of H3O plus remains constant, and pH of the substance or solution does not changes. Similarly, the OH minus ion of water, it again reacts with acetic acid molecule to give acetate ion and water. Therefore, the concentration of H3O plus does not changes, it remains constant, and therefore pH of the buffer solution does not changes. That is about the buffer action. That means that is the property of buffer which does not changes its pH even after addition of strong acid into it, strong base into it, or after dilution, or if it is kept for longer time, pH of the buffer remains constant. As buffer have tendency to restrict the change in pH, therefore it is widely used in different field of everyday life. Therefore, we will discussing on application of buffer solution. Then first one, see here, in biological system buffer is present. In biological system buffer is present. Then see here, biological system means living organism. Then different types of physiological processes takes place in living organisms, and that means in plants or as well as in animals. That is like respiration, digestion, excretion, photosynthesis, and blood circulation or ATP formation. Like different processes, lot of processes, biological processes takes place in living organism, and these processes takes place at a specific pH. In stomach, food digestion takes place in acidic medium, as well as the pH of blood, pH of human blood, it is always lies between 7.36 to 7.42. Then between these pH of blood, most of the biological processes carried out significantly, and if the pH of that human blood changes slightly by 0.2, then it may causes death also. Therefore, in any diseases or any disturbance of biological functions, the saline water, that saline water which contains buffer, and which maintain the pH of blood, human blood, at between 7.36 to 7.42. And that pH of human blood, it is due to the HCO3 minus and H2CO3, that is carbonic acid, that is weak acid, and HCO3, that is bicarbonate ion, that buffer, because of that buffer which is present in blood, pH of the blood, it lies between 7.36 to 7.42, and almost all physiological functions carried out at this pH of blood, and it is maintained because of that buffer, that is buffer H2CO3 plus HCO3 minus ions, that is the acidic buffer. Then see here, second one application, that is in agricultural processes or agricultural activities, buffers are used. Then all of you aware of that soil is fertilized by different manures, that is fertilizers. There are different types of fertilizers, that is carbonate fertilizers, bicarbonate fertilizers, phosphate fertilizers, or organic acids are there, which is act as a manures or fertilizers. Then the salt which is present in the fertilizers, when added into soil, the acid from soil, it forms the buffer and which maintain the pH of that soil and to make that soil fertile. That means depending upon the pH of soil, the particular fertilizer is added into it, or it is maintained to the pH of that soil. A specific type of fertilizers are provided into the soil, and therefore to make the soil fertile. Then third one property, that is in qualitative analysis of acidic and basic radicals. Then see here, there is a practical of detection of or qualitative analysis of acidic and basic radical. Then in qualitative analysis of acidic and basic radical, third A group elements or radicals are get precipitated, that is PPT formation of third A group elements takes place at pH between 8 to 10. That means in basic medium, third A group radicals get precipitated to detect the radicals present in the given salt, and to maintain the pH between 8 to 10, that is basic pH is maintained due to the addition of NH4Cl and NH4OH. Then basic buffer which is added into the during qualitative analysis of acidic and basic radical to detect out the third A group radicals. And at this pH, third A group radicals are precipitated out for the detection, that is basic buffer of NH4Cl and NH4OH is used in it. Then fourth one, application, that is in industries. In different types of manufacturing of products like paper, dyes, drugs, paints, plastic, rubbers, textile industries. Buffer, different types of buffer are used in the industrial processes. Then one more application, that is in medicine. In medicine, or while drug production or medicine production, the buffers are used to maintain the pH of that particular syrup or tablets or the medicines or drugs. Citric acid is added into milk of magnesia. Milk of magnesia is nothing but it is a MgOH twice, that is magnesium hydroxide. And when citric acid is added into it, it gives magnesium citrate. And buffer formation takes place here, which is used in the antacid drug. Then sodium citrate buffer is used in the preservation of production of penicillin. Penicillin, it is a drug which is used on different types of diseases. Then penicillin is preserved in sodium citrate buffer. And one more application of that buffer is it acts as a preservative, that is additives. What is preservative? It is a substance which is added into the food or packed food or cooking food in trace amount, which preserve that food for longer time. That means spoilage of food does not take place easily. During cooking of food, vinegar or few drops of vinegar is used into the cooked food, which preserves that food for longer time. Then during production of jam, jellies, pickles, canned food, that is packed food like potato chips or kurkure, like that packed food. Then preservatives are used into it, and that preservatives are nothing but these are specific type of buffer of specific pH. That is about the application of buffer. Then one more concept we will discussing on it, that is solubility of salts. We have discussed about the different types of salts and nature of these salts. Then there are generally 4 types of salt, that is salts of strong acid, strong base, salt of strong acid, weak base, salt of weak acid, strong base, and salt of weak acid, weak base. And the nature of that salt, it may be acidic or basic, or it may be neutral. Then strength of these salt is also related with the solubility of that salt. Then solubility means, see here, in given amount of water, suppose there is 1000 ml water is there, in which number of moles of salts dissolved into it, and when a particular number of moles added into it, the salt which is in solid state, when dissolved into the given amount of water at given temperature, that means at room temperature, then the salt which is in solid state dissolved when completely, then it behaves like a gas. That means that solution becomes transparent. That means that salt molecule dissolved completely and a transparent solution is obtained here. But if we added salts in excess amount into it, then one stage comes where the number of molecules of that salt does not dissolve into it. That means here, suppose in 1000 ml of water, if 10 moles of salt dissolved completely, and when we add 11th mole of that salt, then that 11th mole, it remains as it is, and that stage or that condition of solution is the saturated solution. Then what is a saturated solution? It is a solution in which maximum number of molecules of salt dissolved in given amount of water at given temperature or at room temperature. And when saturated solution is formed of that salt, then there is equilibria is attained. That is, Ba is the molecule of salt when dissolved in aqueous medium. Then it dissociates into B plus A minus ions, and equilibrium attained between dissociated ions of salt and undissociated salt molecule in aqueous medium at saturated or insaturated solution. Then all of you aware of that the solubility of different salt is different. That means the solubility of sugar and solubility of common salt in given amount of same amount of water is different. That means same number of salt molecule and same number of sugar molecule, it does not dissolve in the given amount of water. That means it is different. Therefore, see here, the one concept you have to concentrate on it, that is different substances, different salts has different solubilities. For example, NaCl, KCl like chloride salts, as well as KNO3, NaNO3 like nitrate salts. These have greater solubility. That means these salts dissolves in large amount in given amount of solvent, that is in given amount of water at given temperature. But at the same temperature and in given amount of water, the solubility of Na2SO4, CaSO4, calcium carbonate or AgCl is very less. That means the number of moles of these salts dissolved in given amount of water at given temperature is very less. That means these are the sparingly soluble salts. That means what are sparingly soluble salts? The solubility of salt is very less in aqueous medium at given temperature at given amount of water. Then these salts are sparingly soluble salt. Then when salts of sparingly soluble salt, sparingly soluble, added into or dissolved into water, that is given amount of water, given amount of water at given temperature, at given temperature, then dissociate in very less extent. Suppose there is a Ba type salts which is sparingly soluble salt. When dissolved in given amount of water in aqueous medium, it dissociate into their ions, but extent of dissociation is very less. Extent of dissociation is very less. That means sparingly soluble salts dissociate feebly or in less extent, and therefore there are unionized or undissociated molecules of salts are there, and equilibrium is attained between dissociated ions of salt and undissociated molecule of salt. That means there is ionic equilibrium is attained or present in aqueous solution of sparingly soluble salt. Then we will discussing on the solubility and solubility product of sparingly soluble salt. Then solubility of salt is measured in mole per dm cube, mole per dm cube, or it is measured in mole per liter. That means, see here, it is a maximum number of moles of salt dissolved in given amount of water at saturated solution of that salt solution, and here equilibrium is attained between dissociated ion, that is equilibrium concentrations B plus and A minus ion and Ba. These three ion and molecules are present at equilibrium. Therefore, these are called as equilibrium concentrations, and equilibrium is attained between equilibrium concentrations of salt at saturated solution of that salt. And if we apply the law of mass action to this equation, because equilibrium is attained here, therefore we can apply law of mass action to above equilibrium. Therefore, see here, K, that is equilibrium constant, is equals to concentration of B plus into concentration of A minus upon concentration of Ba. Then see here, the Ba molecules, that is undissociated or undissolved molecules, are in greater amount, and the dissociated ions, that is B plus and A minus ions, are in very less extent. It is very less extent, and therefore concentration of Ba, that is concentration of excess substance, is always constant, and which is denoted by K dash. Therefore this equation becomes K is equals to concentration of B plus into concentration of A minus upon concentration of Ba. We are putting the value of concentration of Ba. Therefore we get K into K dash is equals to concentration of B plus into concentration of A minus. Therefore K into K dash is the new constant which is obtained here, that is KSP is equals to concentration of B plus into concentration of A minus. Then see here, the KSP is nothing but it is a solubility product. Solubility product of sparingly soluble salt. Sparingly soluble salt. Then there are different types of salts are there. That means there are Ba type salts, B2A type salts, Ba2 type salts, B2A3 type salts, B3A2 type salts are there, Ba3 type salts are there, B3A type salts are there, or Ba4 type salts are there also. There are variety of salts which having a specific molecular formula of that salt. Then see here, generally for these all type of salt we can write the general formula of salt, that is Bx and Ay. That is the general formula for any type of salt. Then see here, Ba type salt, that is NaCl, KCl, AgCl, AgBr like salts are there. That is NaCl, AgCl, AgBr like salts are there. Different types of salts. Ba2 type salt, that is MgCl2, CaCl2 like salts are there. B2A3 type salts are there, that is Al2O3 or Fe2O3 like salts. B3A2 type, that is Ca3PO4 twice salts are there, or here Ba3 type, that is FeCl3 like salts are there. That is general formula for BxAy. That means X and Y, it may be any natural number. Then that BxAy type salt is a sparingly soluble salt. Sparingly soluble salt which dissolved in water dissociate to gives, see here, that is B plus Y ion is there, and formation of A minus X ion formation takes place here, and total number of B plus Y ions, that is X, and total number of A minus ions are, that is Y. That means see here, for example, that is Al2O3, in which here when it dissociate to gives Al3 plus, that is 3 Al3 plus and O2 minus ion formation takes place. Similarly, we can write the dissociation equation of sparingly soluble salt in aqueous medium, in which equilibrium is attained in dissociated ions and undissociated salts. Then applying law of mass action, we get KSP. Directly we can write the KSP is equals to concentration of, see here, B plus Y ion, that is raised to X molecules are there, therefore raised to X, into concentration of A minus X ion raised to Y molecules are there, Y moles are there, raised to Y. Then that is the solubility product of for any sparingly soluble salt. Then definition or concept of solubility product is nothing but in saturated solution of sparingly soluble salt. That means we can calculate the KSP of any sparingly soluble salt when that solution is saturated solution of that salt. Then in saturated solution of sparingly soluble salt, then product that is multiplication of concentrations of constituent ions, that is dissociated ions, which is raised to the equal to their respective coefficients, equals to the respective coefficients. That means here at given temperature in given saturated solution is called as solubility product. Using this formula, we can write the solubility product for these different types of salts and the relationship between KSP and solubility of that salt. Then in next lecture, we will discussing on the relationship between solubility and solubility product of different types of sparingly soluble salt. And thank you.